All right, this is lecture 10. We're going to talk about weather and climate data in the energy industry, and mostly the impact of weather and climate on electric power systems. So lectures 8 and 9 were mostly Khan Academy videos. This is going to be another one where I talk the whole time, and it could run a little bit long, but we'll see. So let's go back briefly to this figure that I've shown before, which just illustrates the complexity of electric power systems, not just on the physical infrastructure side of things, the relationship between generation and transmission and distribution and consumers or electricity demand, but also how macroeconomic conditions feed into things, commodity prices, GDP growth, changes in technology, also regulations. And then we're also constantly keeping track of all these metrics that we use to describe whether or not electric power systems are performing in a way that we deem successful, right? And we judge that by how much it costs, electricity prices, the impacts, environmental or otherwise, that the systems are having, and then reliability. And so at the top here, you can see weather and climate. And weather and climate is super important, and I think it shows this here. In number one, creating demand for electricity. It's one of the primary drivers of electricity or energy consumption is weather and climate. It also directly impacts transmission and distribution systems, and it directly impacts the availability of generation. So it's on both sides of this complex system, and so that's why we're going to spend today talking about it. I'm a little biased in this area because this is the main focus of my research, but the influence of climate and weather on energy systems cannot be overstated. As we have designed them, they are very, number one, impactful on the climate, and that's something that we all pay attention to in terms of the greenhouse gas emission footprint of the electric power industry, but they're very susceptible to variations in weather and climate as well, both on the supply and demand side. And so as we talk about changes in technology, especially the switch towards renewables, in some respects, energy systems may become less exposed or less dependent on weather, at least on the generation side. And specifically, the goal is to really reduce our dependency on water-intensive generation, which is usually thermal generation, so coal, natural gas, but also nuclear. Now, having nuclear in the mix is not necessarily at odds with climate objectives. Certainly not, and there's a lot of people that argue that we need more nuclear as opposed to less, but we're going towards a situation which we're going to have less anyway. But, that said, I think if you're talking about climate change and increasing temperatures, potentially more uncertain hydrology, there's a risk that our energy systems may become more susceptible in other areas. And so we'll just have to see how this plays out. It depends on how the climate changes. It depends on how the technology changes. So here's the scope of weather and climate impacts on power systems. First, some terminology. Weather really refers to, daily temperatures, precipitation, humidity, wind speeds. Climate is referring to the average seasonal conditions for a geographical area. By extreme weather, we're talking about, statistically rare weather events. So not necessarily anomalies, although that can occur, but really high temperatures or really low temperatures or a lot of precipitation or no precipitation, right? So droughts, floods, heat waves, cold snaps, and in some cases hurricanes. So I mentioned before there are two main aspects to how weather and climate can impact electric power systems, and one is on the electricity demand side, so it directly impacts heating and cooling demands, and then the other side is the electricity supply side. So we're not just talking about generation here, we're talking about system infrastructure at large, so that includes transmission lines, as well as power plants, or more conventional thermal power plants. Transmission lines are impacted by high temperatures. Thermal power plants are impacted by loss of cooling water. That can happen because of drought or high temperatures or both. Variable renewable energy, so wind and solar and hydropower. These are directly tied to weather and climate. And so a future in which we are more dependent on these is going to leave us in some cases more susceptible to unexpected changes in weather and climate. And then fuel prices as well, especially natural gas. Natural gas prices have historically been impacted by extreme weather, particularly hurricanes that disrupt natural gas production in the Gulf region of the United States. So here's an illustration of why weather is important for driving electricity demand, at least on the retail basis. So this shows average annual electricity consumption in U.S. homes, and it's ranked by device, right? And so number one here is air conditioning. So a lot of our electricity consumption in the United States comes from the use of air conditioning during summer times, which is driven purely by temperatures. And you can go down the list here and also see space heating is down here as well. Now, a lot of the U.S. uses other forms of energy besides electricity for heating, including oil and natural gas, but a lot of people do use electricity as well. So you got space heating, but mostly cooling as a big driver of electricity consumption. And this is something that we've seen before. So we've investigated a little bit through some data mining activities looking at temperature and electricity demand that there is not a linear relationship between temperature and electricity demand. It's nonlinear. And it depends on, the shape of this curve depends a little bit on where you live in the United States. But mostly where you live depends on what range of temperatures you experience. And so in general, really low temperatures and really high temperatures result in higher electricity demand. But there's this sweet spot in the middle where it's 65 or 75 degrees, where nobody's using heating and nobody's using cooling, and electricity demand is at its lowest point. So because of this nonlinear relationship between temperature and electricity demand, we can't come up with like a linear regression that describes, the amount that electricity demand increases for every, 1 degree increase in temperature. And so instead we have to break up temperature into what we call heating and cooling degree days if we're going to model the relationship between temperature and electricity demand. So a degree day is this comparison between the outdoor temperature, the outdoor ambient temperature, with a standard temperature of 65 degrees, with the assumption being that anytime it's 65 degrees, no one's using heating, no one's using cooling. And the only way you generate a heating or cooling degree day is if you go above 65 degrees or below 65 degrees. And the further you go away from 65 degrees, the more degree days you create. So for example, the equation at the bottom here for a heating degree day is the max of this function that's in the parentheses. And the max operator here is similar to how we use max in MATLAB, right? So it's taking the maximum value of what's in the parentheses, which is the choice of 65 minus T and 0. And what this effectively does is make sure that heating degree day, this value never is negative, right? Because if you're taking the max of anything and 0, it's never going to be negative. And so here you create a heating degree day as long as T is lower than 65. So, for example, if T was 60 here, you'd say 65 minus 60 is 5. So the max of 5 and 0 is 5. And so if it's 60 degrees on average tomorrow, then tomorrow we would say there's the 5 heating degree days associated with tomorrow. And that indicates some, but not very much demand for heating. Like some people might turn on their heater if it's 60 degrees. a lot of people would just sort of grin and bear it. Now with cooling degree days at the bottom, you can see it's a similar equation, but the T and the 65 are switched. And so what that does is it means that you're only creating cooling degree days when the value of the ambient temperature is above 65. So for example, if it's 90 degrees tomorrow, then we say 90 minus 65 is 25. And so the max of 25 and 0 is 25, and we've created 25 cooling degree days for one 24-hour period in which the average temperature is 90 degrees. And so that indicates pretty substantial cooling demand. So a lot of people would be using their air conditioning. So we can also think about how these values for heating and cooling degree days vary geographically or spatially. And so this is a map that was created by the US EIA. It's divided the US into several different regions. This is clustering, right? These are regions that are being clustered based on their heating and cooling degree days. So what's shown here is that in darker regions, so the upper Midwest and the Northeast, these are regions that experience much higher cumulative heating degree days during the year. So what that means, they have colder winters. And the lighter colors, so the Southeast where we live, experience relatively low numbers of heating degree days. So we have mild winters and relatively low heating demands throughout the year. We can look at the same thing in terms of cooling degree days, and in this case, the trend is sort of switched, right? So we have the darker colors in the south and the southeast, and the lighter colors in the north. And so the northeast exhibits the lowest annual cooling degree days by census region, and the south exhibits the highest, right? So we take our big energy hit in terms of consumption during the summer as opposed to the winter. So degree day data, which you can calculate directly from mean daily temperature data, is used to assess the heating and cooling needs based on time and season for a given region. If you wanted to translate it directly to electricity demand, you could model it. You could come up with a linear regression that would incorporate heating degree days and maybe some other stuff as well. So you take advantage of the known relationship between heating degree days and electricity demand. And because you're accounting for degree days separately, right, you can actually create a linear regression, and you don't have to worry about this nonlinear relationship between temperature and electricity demand. Now, the one important consideration when doing that is that you weight the degree days for given areas by population, right? So if you were looking at two different states, and one had a much higher population than the other, then the increase in electricity demand per degree day is going to be much higher in the state where there's a lot of people that would be potentially using an air conditioner or a space heater than the state in which no one lives, right? And so that's true even within utilities control areas. So if I'm Duke Energy and I'm trying to figure out how much electricity demand I'm going to have during the day, I would create time series of degree days for a bunch of different places in North Carolina, and I would put them all in a linear regression model, but I would weight those temperatures by the number of people that live there, right? So Charlotte would count more, Raleigh would count more, what the temperature is in Charlotte and Raleigh, than it would in Mebane, where I'm from, or Southern Pines or something like that, where there are fewer people, or up in the mountains. So this figure shows the relationship between heating and cooling degree days and electricity demand in the southeastern United States. So in black you have electricity demand, gray you have heating degree days, and red you have cooling degree days. And so the really big increases in the black line electricity demand are the summertime, and you see slightly smaller peak times in the winter, right? So this starts in the winter, you see it increase and then go back down during the spring, it goes up during the summer, it goes back down during the fall, and then it repeats itself. And you can see that the winter peaks are associated with high heating degree days, and the summer peaks are associated with high cooling degree days, or relatively high. And what should pop out at you here is that we experience a lot more heating degree days than we do cooling degree days, but cooling degree days have a much stronger influence on electricity demand, right? And that's because we rely completely on electricity for cooling requirements, and we rely on other sources of energy like natural gas and oil to satisfy heating requirements. So that shows things on a daily and seasonal basis. Obviously, on an hourly basis, this matters as well. Temperature differences are big drivers of electricity demand on an hour-to-hour within-day basis. So we've looked at this a little bit as well. So in the summertime, at least in the southeast, peak electricity demand occurs during the late afternoon. It's associated with increases in cooling demand because that's the hottest part of the day. And in the wintertime, peak electricity demand occurs in the morning and the evening, and that's associated with economic activity, but also heating demand, right? So the warmest part of the day during the wintertime is the middle of the afternoon, late afternoon, and so heating demands are lower then. Okay, so I think we've taken care of the impacts of weather and climate on electricity demand. Now let's talk about the impacts on electricity supply. So we'll start with the generation mix. Obviously weather here is going to directly impact the availability of hydropower. In the west it depends on how much it snows. On the east it depends on how much it rains. Wind also is heavily influenced by weather and climate. Solar is too, and we'll talk a little bit about why it's a little less obvious. So you may think that a relatively small fraction of this total mix is actually impacted by weather and climate, but in fact all of it is, because nuclear, coal, and natural gas power plants use a lot of water for cooling requirements, and they're impacted by periods of water scarcity, but also high temperatures. So this susceptibility of different types of generation to weather and climate varies on a regional basis because our dependence on different types of generation varies on a regional basis. So if you're in the Pacific Northwest, most of the time you're living the dream. You have mostly carbon-free energy because you're entirely dependent on hydropower, or mostly dependent on hydropower. Except when you're in a drought, and then you're screwed because the main energy source that you rely on is completely dependent on how much water is available. And in some cases, actually, who gets screwed is California because of how much hydropower they import from the Pacific Northwest. If you look in the southeast, we're heavily dependent on coal and nuclear. These are very water-intensive technologies, so anytime we have a really severe drought in the southeast, a big part of our thermal generation, coal and nuclear, is threatened by a lack of availability of cooling water. So weather also impacts transmission. And we talked a little bit about, in the Grid 101 or the grid overview, why we have AC systems, and it's because we want to minimize line losses, and the way we minimize line losses is by ramping up the voltage to very high levels so that we can transmit the same amount of power with very small current. And the reason why we want very small current is because we lose power as a function of current and the resistance of a line, and that's what this equation shows you, right? So the power losses in an AC transmission line are equal to the square of the current times the resistance of the line. And so we're doing what we can by ramping up the voltage to minimize the value of I here. But the other side of this equation is the resistance of the line. And it turns out that as you increase the temperature, the ambient temperature, you increase the resistance of the line. And so there's an equation here that shows you the resistance at a certain temperature is equal to the resistance at some sort of baseline temperature times this equation in brackets, 1 plus alpha times the difference between those two temperatures. So basically this is just saying that the resistance of a conductor increases linearly proportionally to whatever this alpha value is, the temperature coefficient. And this temperature coefficient varies depending on what type of metal we're using to create the conductor. So some metals have higher values of A, some have lower. The higher the value of A, the higher the resistance goes as you increase temperature. So this is sort of an interesting figure or set of figures that puts a couple different concepts together. I mainly want you to look at the top one. So this shows the influence of temperature and wind speed on the temperature of a conductor, which we've said is linearly related to resistance in the conductor of an AC transmission line. So at baseline, which is this black horizontal line that goes across here, you see the conductor temperature is, 35 degrees or something like that. Now, if sun is available, then the temperature of the conductor increases to this orange line. And so because the temperature of the conductor increases, that means its resistance increases as well. Now, if wind is available at the same time that sun is available, you only have these intermittent periods of high conductor resistance, and the rest of the time the wind is cooling off the conductor and resulting in temperatures that are around the baseline, and in some cases even lower than the baseline. And if wind is available but there is no sun, then we're operating on this lower green line. So that's transmission stuff. Let's also talk about cooling water issues at thermal power plants. I've alluded to this a little bit. Thermal power plants means any type of power plant that is using a source of heat to either create steam that spins a turbine, or uses hot air, in like a natural gas combustion turbine to spin a turbine as well. And what we're really concerned about in terms of cooling water issues at a thermal power plant are the steam-based power plants. And so this would be basically every coal power plant, every nuclear power plant, and most natural gas power plants. So you have a heat source coming in here. Qin is the heat that you're bringing in through fuel, right? So whether that's nuclear fuel or coal or natural gas, you either combust it or it's part of a nuclear fission reaction that creates heat and heats this blue water up until it gets hotter and turns into steam. And then the steam is passed through a turbine, and the pressure on the steam is lowered. And so the expansion of that steam spins a turbine, which is connected to a magnet and within a coil, and it generates an electrical current. And so that steam, which by now is red and now turning into purple, is then cooled down. And it's cooled down using some sort of condenser coil here, which is this squiggly teal line going back and forth here. And through this condenser coil is being passed cold water that was drawn directly from a river or a lake. And so that river or a lake absorbs a lot of the heat from the steam and then is sent back out of the power plant, either into a cooling tower where it cools down through evaporation, or it's discharged directly back into a river or lake. But the steam has been cooled down a sufficient amount that it turns from steam into water, but it's still hot water, right? So you don't want to lose all the heat. You just want to turn it back into water so that it can be passed back through here, back through a pump, and then have the cycle continue. Now, what we're sort of concerned about is this larger interaction in this red dotted line here, the cooling system of the plant itself. There are a couple ways that thermal power plants can experience problems related to cooling water issues. And the first is if lake levels or river levels fall below the minimum depth of the plant intake. So power plants have these big straws that they use to pull in water for their cooling systems. And if the water of a river or lake goes below that, there's nothing you can do about it. You just have to shut your plant down. So while it is possible that power plants experience outages because water levels fall below plant intakes, it's not very common. What happens more frequently is that water temperature issues in the cooling water body itself cause power plants to curtail or shut down. And so let's think about why we need a cooling water system again. It's a mechanical efficiency issue, but it's also a safety issue. We want to absorb a significant amount of heat from the steam that we just created, turn it back into water, and take a lot of this heat away from the power plant. And so let's think about how much waste heat is generated by a power plant. So let's say we have a power plant that's producing a certain amount of power, kW. So kW, this is how much electricity, we're assuming that the plant is producing at its maximum capacity, so 500 megawatt hours or something like that. So we can put that same amount of electricity into an amount of heat, right, that's required to generate that electricity. This is the heat rate, right? It's the amount of fuel or heat content of fuel in million BTUs that's required to create this same amount of electricity, right? And then once we've converted this amount of electricity that we're producing to an amount of fuel that's needed, or heat content of fuel, then we can figure out how much of that plant how much of that energy is converted to electricity, and how much of it is just wasted. And so that's what this N total variable is. So this tells you how much of that total heat input, how much of the total heat or energy that's included in the natural gas. And once we've done that, once we figured out how much waste heat is generated by the power plant, then we can talk about how much of that waste heat actually needs to be absorbed by the cooling water. So not all of it needs to be absorbed by the cooling water. Some of it could be just vented to the air, or used for some other purpose. So the amount of the heat that is not discharged by the cooling water is this. So if we're saying that 100% of the waste heat is not discharged by the cooling water, then this whole thing becomes zero, right? But the reality is that a significant amount of the waste heat actually needs to be discharged by the cooling water. So the value of alpha here could be 0.6 or 0.7 or even higher. So we have now an equation for how much waste heat we need to be absorbed by cooling water on the left-hand side, and on the right-hand side we can think about how much heat, how much water, how much, like the flow rate, gallons per second, or there's probably a better set of units to use to describe that, we need to absorb that amount of water. And so it's a function of how much water we're going to pass through the heat exchanger at a given time. It also depends on the heat capacity of the water, so the ability of water to store heat, and also the density of the water, and then also the differences in the temperature between the water that we're taking in and the water that we're going to discharge, right? So you can sort of think we want both of these to be equal, right? Both sides of this equation to be equal. And one of the big trade-offs here is between the term here on the right, the T out and minus T in. If you want that number to be smaller, or if it has to be smaller, right? For example, if you are taking water in that's 25 degrees and you are legally required to discharge water that was no more than 28 degrees T out, then the amount of water Q here has to be a lot larger than if your T out minus Tn was 10 degrees, right? If you could, if the difference between the temperature of the water you intake and discharge could be 10 degrees, right? So a tight limit on the T out versus T in here has implications for the amount of water you have to be withdrawing at any given time to absorb that same amount of heat. And so this is part of the problem. In many parts of the country, there are regulations on what T out can be, and sometimes there's a specific rule about what the difference between these two can be. For example, 3 degrees or 10 degrees. But often there's a strict rule about what this can be. Because as you increase temperatures, you are having a stronger and stronger environmental impact on whatever water body you're discharging the heated water back into. One of the main concerns with discharging really hot water into rivers and lakes is that dissolved oxygen decreases, because as you increase the temperature of water, its ability, the solubility of oxygen decreases. So hot water has less oxygen in it. So as you increase the temperature of the water, fish literally can't breathe. So let's think about what happens during a drought or a heat wave. And so we have this same equation here where this is the amount of heat we need to be absorbed by the cooling water system, and whatever happens on the right hand side, we need it to equal what's on the left hand side. So in a drought during a heat wave, so you're concerned about two things, right? You're concerned potentially about the difference between the input and the output temperature, but you're also concerned here about running into this upper limit, right? And so during a drought and a heat wave, the main thing that happens is that Tn increases, right? The water temperature in the river or lake that you have your water intake straw in, so the water that's being sucked into the power plant, is hotter. right? Because there's less water in a river or lake, and it's usually summertime. And so as Tn gets bigger, then this whole value here on this side gets smaller, right? This potentially gets smaller, but also you're getting closer and closer to this number. And so the only thing you can do to keep this whole right side of the equation equal to the whole left side of the equation is to increase the value here, the amount of water that you're withdrawing. So remember, you're in a drought. So if you're in a drought and the only way you can keep your plant absorbing enough water is to suck in more and more water, then you may run up into a limit of that, right? And so at some point you may have to decrease. The only option to keep these both sides of this equation equal is to decrease this number, right? To decrease the amount of energy you're producing. And so that can happen gradually, where a power plant will curtail by 10% or 25% or 50%. But at some point it has to be shut down completely, especially if the input temperature of the water reaches a certain point. And so this whole issue has become one of increasing concern, or at least an area of increasing study, and I sort of study it, but there's a lot of people that have looked out into the future and said, all right, well, we know this is an issue now. What's it going to look like in the future under climate change, right? Because we know we're going to have higher temperatures, potentially more frequent and severe droughts. How much more often are we going to run into situations where the thermal power plants we have don't have enough cooling water, or they have enough cooling water, but it's not a cold enough temperature to actually be useful. And so these are results from a study that was in Nature Climate Change that looked at this, right? So they projected out into the future in the 2040s and the 2080s under two different climate change scenarios. One which is okay for us, and one which is like the worst case scenario. And you can see that when you get out to the worst case scenario in the 2080s, there's a really big increase in the number of days per year, which is what this color is showing, where the water temperature is beyond the temperature limit for operating a power plant, right? So this is saying that a big part of the southeast in the 2080s, under the worst case climate scenario, more than 60 extra days a year, we'd have thermal power plants experiencing prohibitively high water temperatures. Okay, so that's impact on thermal cooling systems from droughts and heat waves. The other issue that we've run into recently is really, really cold snaps. And this is an illustration of the polar vortex. The polar vortex just refers to this regional climate circulation that extends down beyond the normal bounds of this polar activity. I'm sure I'm not describing this in a very articulate way, but this, on the right hand, you see what's normal, right? This mass of very, very cold air over the Arctic that's for the most part sort of kept there, and then what's not typical is on the left, where the bounds of this sort of extend and they get more wavy, and in some cases they can extend down pretty much into the middle of North America, which is what happened in the January and February of 2014. So when this happened, it's in the wintertime, and wintertime is a period of relatively high electricity demand, but not super high, at least not compared to the summertime. This caused huge problems. and it was pretty unprecedented. In a lot of systems, they experienced electricity demand during the wintertime that they had never experienced before. And so that was the sort of the first effect, is that it increased people's electricity demand. The other issue is that since we've been switching from coal to natural gas, power systems in general are more dependent on natural gas. And so at the same time that you have increased electricity demand, and you have increased demand for natural gas from the power sector, you also have people experiencing wintertime temperatures that they've never experienced before. They're really cold. So people that use natural gas and even oil heating dramatically increase their demand over a relatively short period of time as well. So you have now competition over natural gas from the power sector and the heating sector. And then the last part of this is that it got so cold that a lot of these power plants that were offline, that they had to turn on relatively quickly to meet this increase in electricity demand, physically couldn't start, right? Just like the first day in the spring when you have to cut your grass and the lawnmower won't start. And so as a result of all three of these, you had really dramatic increases in electricity prices. And you can see on the top, this goes from August 2013 to the end of February in 2014. And it looks like electricity prices are flat through August all the way through basically December. They're not flat. It's just that the scale here on the y-axis goes from $0 to $600. The reality is that the polar vortex just caused like monumental increases in electricity prices over a relatively short period. And just to put that into some perspective, at the bottom, this figure down here shows you electricity prices over the last 7 years. And you can see they really crashed in the wake of the financial crisis. People were using less electricity. And then the price of natural gas has been so low because of relatively low demand, and fracking really reached a low point in terms of electricity prices in 2012. So it's been pretty flat basically for 6 years, and then all of a sudden you have the polar vortex down here. Caused a lot of concern about the readiness of electric power systems to deal with really extreme weather events. So I think this is the last thing we'll talk about: variable renewable energy production. Obviously, this is directly impacted by weather and climate. Hydropower, wind, and solar are all directly impacted by changes in weather and climate. So I like this figure. This is U.S. production of hydropower over the last 70, 80 years. Had very little starting in 1950, and then we went on a really big building spree as part of the New Deal and all sorts of stuff. The Bureau of Reclamation, the Army Corps of Engineers, we built dams all over the arid West for water supply, for flood control, but also for hydropower production. And really, since the mid-1970s, we haven't been building any more dams, right? And so all the rest of this variation you see is just year-to-year changes in how much it snows and how much it rains. And who experiences the brunt of this uncertainty? It is the Pacific Northwest, right? So in a lot of ways, they're blessed. If you're from there, you can ignore the thing I'm about to say, but if you're not from there, don't ever listen to someone from the Pacific Northwest who takes a holier-than-thou attitude about carbon emissions from their electric power systems, right? The reason that they have very little carbon emissions is because they are naturally blessed with incredible hydropower resources. It's not because they went out of their way to design this perfect low-carbon system. It's just because of dumb luck. So most of the time, they have relatively cheap electricity that's relatively carbon-free. The issue is that when they experience drought, significant drought, a big chunk of their electricity generation goes away. So the most famous part of this, the Pacific Northwest hydropower system, is operated by Bonneville Power Administration. This is sort of a branch of the federal government. It's a weird organization. But this is the Federal Columbia River Power System, which extends through Canada, Montana, Idaho, Washington, and Oregon. And all these dots are dams. Blue ones are owned by and operated by the Corps of Engineers. White ones are operated by the Bureau of Rec. Collectively, this is about 23 gigawatts of hydropower capacity, which is equivalent to all the capacity owned by Duke Energy Carolinas, and it provides about 60% of regional electricity demand. Now this system is snowmelt dominated, which is a lot different than hydropower systems on the East Coast that like Duke Energy owns. Now the cool thing about having a snowmelt system is that a lot of precipitation falls as snow, and then it's stored throughout the wintertime in the mountains, and then it melts in the summer, starting in the midsummer and goes basically through August. And so the cool part of this is that you have water that's being naturally stored in a frozen reservoir that melts basically when you need it in the summertime. But the issue with this particular system and how it's operated in the Pacific Northwest is that because of climate change, the timing and amount of water that melts or comes through the dams is going to change. So on the left-hand side here you have our more or less current climate situation, and on the right hand a really sort of catastrophic climate warming scenario. And this is on the y-axis runoff or stream flow really at the mouth of the Columbia River downstream on both y-axes. And you can see under current conditions, it's snowing all in this period, right? It's snowing all here, and then the snow in the mountains melts, and the water coming off the hill slope melting into rivers being passed through dams accumulates and reaches this max point in June or July. And then it dissipates back towards the fall. Under climate change, you see a lot more stream flow here because less precipitation is falling as snow. More precipitation falls as rain, and just throughout the year, because you have warmer temperatures, and just immediately runs into the rivers. And then you have a lower peak here in the summertime. Wind energy is obviously impacted by weather and climate. I think regional climate is really maybe more important than in terms of resource development, because there are just some parts of the country that are more wind rich than others, and that's what this map shows. Likewise, there's a significant difference. I guess this is definitely weather related. It's more, I guess, of a physical geography issue where you have higher, more consistent wind speeds off coast, offshore than you do at land-based sites. But you do have significant year-to-year changes in wind power production because of climate and weather variability, and this is difficult to plan around. If you're thinking one of the advantages of renewable energy, I know it's variable, but year to year you know what you're going to get. That can be not quite true. And in fact, in some parts of the Midwest, we're sort of right now in the midst of this prolonged wind drought. And what makes this really hard, I think, to predict is that the amount of information that we have about wind speeds historically really doesn't go back that far. So what you'd really like to do is see like hundreds of years of wind data for the Midwest to see, what the distribution is, and historically, how often do we have wind droughts and wind surpluses, and we really just don't have much of information in that area. So obviously, there's seasonal wind variation as well. This is for one particular wind farm, so this is going to be different. The nature of this seasonal variability, where in this case it's wind is highest in the winter, lowest in the summer, is going to be very specific to whatever region you're looking at. And that's what I was just referring to. This shows seasonal wind variability as a function of geography. In the Northwest, you see that is, I guess, the West Coast in general looks a bit different than the rest of the United States and the East Coast. But every region is a little bit different, and you have to think about how this sort of naturally overlaps with electricity demand patterns to figure out whether, how useful wind is at meeting seasonal changes in electricity demand as well. You also see hourly wind variability play out in fairly regular diurnal patterns. I mean, obviously, if you have weather systems moving through, you can have wholesale shifts in the availability of wind over a couple days. But especially when you're talking about the interaction of a water body and a land mass, changes in air temperature and pressure end up creating fairly regular diurnal patterns in wind availability as well. And then, of course, you have hourly wind variability that can change by season as well. And this just gives you an idea of how for two different sites, each month of the year has different hourly wind variability. And again, this is this figure shows coefficient of variation, which is sort of like standard deviation. It's the standard deviation divided by the mean. So this gives you an idea of how variable wind energy is during the day by season. And that sort of matters. I think, the idea here being that if you had a lower coefficient of variation, less variability in hourly wind production, it would be easier for power systems to incorporate. I think that's a little oversimplified. If you had a lot of variability, but it naturally overlapped with the variability in electricity demand that occurs, then it's awesome, right? That's exactly what you want. So, but I do think, to some extent, larger variability in wind production during the day is a little more difficult for power system operators to incorporate. And so this gives you an idea that, some months may be harder than others for power systems operators to deal with wind production. So one of the interesting things about power system operations and planning with regard to the integration of renewables is one of the big challenges is how we get to this point where we can directly replace base load coal generation with variable renewable energy like wind and solar. And there's a number of challenges to doing that, and the thought is that through the combination of storage technology, whether it's batteries or something else, and demand response, so people changing when they're consuming electricity to naturally accommodate the availability of renewables, we could do this, or we could do it enough. And not enough attention gets paid to the value of really good system planning in terms of how you combine different types of variable renewable energy resources to complement each other. So you're reducing the variability and uncertainty just by putting different good combinations of things together. And so part of this is how you space renewable energy projects to take advantage of less covariance in when they're producing energy. Part of it's taking advantage of what we call the law of large numbers. And so here, this is an illustration of that. So we're talking about the average value of rolls of a 6-sided dice, right? as a product of the number of rolls, right? The number of trials, all the way up to 1,000 here. And so the long-term average, right? The numerical average expected value for a one roll of the dice is this, 3.5, right? If you average 1, 2, 3, 4, 5, 6, you get 3.5 as your average value. So that's your expected value for 1, 2, 3, 4. It doesn't matter how many rolls of the dice. The average value is expected to be 3.5. So the actual average value of real rolls of the dice vary quite a bit from that, especially once at first when you're rolling dice. I mean, if you think you start rolling dice and you roll it maybe 10 times, you might have an average of those rolls that's much lower or much higher than what you think the expected long-term value is going to be. But as you roll the number of the dice more and more times, that value, that average value, converges. And that is the law of large numbers. It's just this sort of clever way of saying it's inevitable that if you roll the dice a number of times, eventually the average value converges to what you think it's going to be. And we can sort of view. So this illustrates on the bottom the cumulative electricity production from 15 wind turbines, right? And it looks like this is normalized to the mean, right? So the y-axis means a little bit less in terms of it's not actually actual electricity production, it's normalized to whatever the mean on the bottom is and the mean on the top. So the bottom one, 15 turbines, is pretty variable, but the top is much smoother here. And this, you can notice the scale here, we're talking about seconds, right? And so this is a clear advantage. You know, if you're a power system operator and you're worried about experiencing pretty significant increases or decreases in the availability of wind, you know, over a period of seconds or minutes or even hours, then one possible solution is to simply build more wind turbines and to space them in a way so that you don't have all the wind turbines experiencing the same increases or sudden decreases at the same time. And we see very similar things with solar as well. So you just get benefits. Here you have one solar plant is this blue dotted line. You have two solar plants together. And again, this is normalized output. 2 solar plants, 6 solar plants, 25 solar plants. And as you get closer and closer to aggregating solar over an entire region, you get closer and closer to what you sort of expect solar power production to be during the day. And the reason why not every plant has this nice half-moon shaped curve is because of cloud cover, really. I mean, you have certain individual plants being directly impacted by what's going on right above the solar power plants, but if you aggregate that over an entire region, a lot of that individual variability goes away. So with wind and solar, it's a little tough when you're talking about just building more building more solar panels or building more wind. It's not guaranteed to give you this benefit, because if you're building solar panels right next to each other, if you build 200 solar panels right next to each other versus 200 solar panels all separated by a mile, then you're probably going to get more benefits in terms of reducing variability in the situation where you're building solar power plants that are all separated by a mile. Because if they're all right next to each other, whenever it's cloudy, they're all like under cloud cover, right? So when you're thinking about planning renewable energy systems, you have to take advantage of this relationship between distance on the x-axis here And correlation or covariance, the degree to which output from two power plants is similar on a day-to-day or hour-to-hour basis, right? So what this is basically saying is that the closer you are, so the closer to zero here on the x-axis you are, the more correlation there is up here on the y-axis between the output from a solar power plant. And so to really take advantage, to get to lower levels of correlation, you have to build things further away from each other. And so this can be a challenge. But when you're talking about distributed solar, I think there's a huge opportunity for utilities to make things easier on themselves by taking advantage of relationships like this. So actually, maybe this is the last thing we're going to talk about is the potential impact of extreme weather on fuel prices. And this shows you oil refinery capacity, which is similar to natural gas refinery capacity in the United States. The size of the capacity is equivalent to, or is represented by the size of these dots. And you can see a lot of oil and gas refinery capacity is concentrated in the Gulf Coast region. And we also see natural gas pipelines. A lot of them are extending out from, Texas, but also the Gulf Coast region. So a lot of activity in terms of producing, refining, and then transporting natural gas to places throughout the U.S. that use it for heating and electricity production is concentrated in the Gulf Coast. Now this becomes an issue when you have Gulf occurring hurricanes, and this is the projected path of Hurricane Katrina, maybe one day out from making landfall. I'm not exactly sure. But you can see that this is a big concern, is projecting how this is going to impact oil and gas refinery operations. And it turns out it had a huge impact. On the left y-axis here, you see oil production. On the second y-axis, you have natural gas production. And these are losses, right? So the higher you are up on the y-axis, the more production you're losing because of a hurricane. And so you can see they're tracking several different hurricanes. Bonnie and Charlie, there's a little blip in production. Francis, Ivan, really big blip in production. And then you get down here to 2005, Katrina was huge, right? Katrina was really unprecedented in terms of how much oil and gas production was lost. Over a relatively short period of time, you're talking about the immediate impacts lasted about a week. They had recovered about 50% of their losses by the end of the first week, but then those losses persisted for some time. And so this shows a similar figure. So this is days after landfall here on the x-axis, and then an amount of shut-in production, so capacity that they cannot realize following hurricanes Ivan, Katrina, and Rita. And so you can see Katrina and Rita are sort of grouped together here, and green is oil and blue is natural gas, and I guess this is Rita here, and then, or maybe I can't remember which came first. Katrina came first and then Rita. I can't remember, but you can see that production, for Ivan, the losses dissipated, and really we were back down to normal, or close to normal levels. Within about 2 months, and this shows that even 30 days after Katrina and Rita, or at least the first hurricane, I think the second big blip is the second hurricane, you had really extended periods of time of significant oil and gas losses. So that's it. That's an overview of how weather and climate impacts energy systems. These are all the references that were used. And we can talk about this as much as you guys want to in class. I'll prompt you and see if you have any questions. Okay.